Okay, so section 5.6 and it's page 276 is where things start. However, I don't like the way they do it, so you better pay attention to the video. Pay attention to my words. I think that the people who wrote this section don't really know what an inverse function is. So I'm going to give you my wisdom instead of this. We're starting, when we actually use the book, we'll start with example 2, which is clear over on page 277. But I'm not willing to start there yet because I think their introduction is very bad. I think it's not only a bad way of doing it, it's incorrect. So here's what we're going to start with. What we're going to talk about is function inverses today. And by the way, if the function is this, then its inverse will be written like this. And it does not mean reciprocal. That does not mean that you put 1 over it. That's not what it means. It's an unfortunate use of this again. It means the inverse of f. And what inverse means, here's your definition right here. The inverse, the function and its inverse, all it does is makes x's y's and y's x's. It just switches places. So that's where we're going to start. Is with a function. Well, I don't know about a function. I'm just going to call it a relation. We'll decide if it's a function or not. It's a relation, and it's just going to be a set of countable points. And not very many of them either. We'll put some up here. 3, -2, 1, 7, -5, -6, 2, 8, -8, 3, and 1, 4, 0, -5. So that's what I'm proposing, is a relation. It's just that all it is, a bunch of points that we would plot on that grid and we could get a picture of it, which I'll do in a few minutes. But here's something that you're going to be required to know when you take the ISAT test in April. A function has 1 y for every x. In other words, here's a better way to think about it. Functions have unique x's. The x's are never used more than once. If it's a function, x's are unique. Y's can be repeated all you want, but x's are unique. X's can only be used once. So, is this a function? Yeah. Yes. If this is the complete relation and you're trying to decide if it's a function or not, you look at the x's. If any of the x's are duplicated, then it's not a function. None of the x's are, so I'm going to go ahead and call this f of x, because we've decided that it is a function. Its inverse, which may or may not be a function, but this is how you write it. If the original function, its inverse may or may not be a function, but we still write it f -1 x, we say f inverse, and all it is this set of points. So, now that we flip them all over, is this a function? No. Where's the fail? -5. Yeah. -5 goes to 7, -5 also goes to 0. So this, even though we call it the inverse of f, we decided this was a function, but its inverse is not. Still, that's the way we reference it. That's the way we refer to it. All it means is that x's and y's switch places. Let's see if you can do this. See if you can remember this, I hope. What is the domain of the first one? What does domain mean? Yeah, it's the x's that are in it. Sometimes it's an infinite set. Sometimes we have to say the domain is x's which are greater than or equal to 4. You know, and that includes billions of them. But in this particular one where the points are countable, we call them discrete. You can count them. You can list the domain. What is the domain of f? Try to see if you can arrange them. It's not all real numbers. The domain of f in this what I have up here on the board. See if you can arrange them from smallest to largest. Talking about the x values, because that's what domain is a list of the x values. -8.
0.
Sorry? 0.
1, 3, 4, 7.
Is that it?
There's 2 4s. Oh, wait, no.
There better not be 2 4s.
Oh,
There's 1, 2, 3, 4, 5, 6, 7 points, and there were 7 unique x's. 1, 2, 3, 4, 5, 6, 7. Okay. Now, I'll do the range of that in just a minute. But what is the range of this inverse down here? Range means the y values. What's the range?
Same.
Oh, that's a very important thing, folks. The range of this was the domain of this because x's became y's and y's became x's. So the range of this is an easy list to make. We don't even have to look at it. Okay, so what's the range of the top one? And by the way, when you list them, you don't list the repeats more than once. You list each number one time. What's the smallest one? The range is a list of y's, people. -5. Okay,
1, 2, 3, 4.
is that it? There should be 6 of them, right? Because the 5 was duplicated, the -5. Okay, so what's the domain of this? Same thing. That's an extremely important notion, and it's not very hard. As you can see, you guys came up with it very quickly. It's really, really important that you understand that if x and y switch places, then domains and ranges switch places in the inverse. You okay with that? Now, graphically speaking, this is how it works out. Sorry if that made you dizzy. Okay. People on the video can't see this, but you guys can. Can somebody read me the points one at a time? Wait for me to count one before you give me the next one. Of F, what are the points?
3.
3 what?
3 -2.
1, 2, 3, 1, 2. Okay.
4 1.
Okay, there's 4, 1. Okay.
7 -5.
4, 5, 6, 7. 1, 2, 3, 4, 5. Okay.
-6 2.
Okay.
-8 3.
6, 8, 3. Okay.
1 4.
Okay.
And 0 -5.
Okay. So I'm going, that's a funny looking thing. Yeah, I just randomly chose numbers, by the way. There's nothing important, nothing, you're not supposed to recognize anything here. So now give me the inverse. I'll mark it in pink.
-2 3.
Okay.
1 4.
4, 4.
1 4.
Sorry?
1 4.
1, 4. Right there?
Yeah.
Oh, sorry. Really? 1, 4?
Mhm.
Well, the other one was 4, 1. I guess that was out.
No, there's a 1 4 here.
Okay, all right.
-5 7.
There can't be. Did I switch those right?
Yeah, you did.
Yeah, there's a
Yeah,
4,
because there's
1,
a 4 1 over 4, so then.
Okay, all right. I had a confusion for just a second, but I see how it's going to work out. Okay, so give me another one.
-5 7.
Okay.
2 -6.
Okay.
3 -8.
Okay.
4 1.
Okay.
And -5 0.
So you look at those and you go, I don't know if I see that or not. You're going, let me show you something else. Let me get another piece of chalk, just a minute. If I put a particular line on here, you start to see how these are related graphically. It's kind of hard to tell when they're just thrown up there like a shotgun. What have I not used? I got blue and pink. Blues, I guess. Hope you can tell the difference between pink and purple. If I put this line on this graph, this line right here, does that help your eyeballs see the relationship at all? Can you see how this pink point right here and this blue point are related across that line? And when you jump across this line, it is the line y equals x. It's got a slope of 1, it's got a y-intercept of 0. It's the very simplest possible line that there is, slanted line anyway. This is called the line y equals x, and it's a reflector. Notice that this pink and this blue are reflections right across the line. And because it is, what you do to get one from the other is you count diagonals. That would be 1, 2 and a half, 1, 2. Did you catch that? You're counting diagonals?
Yeah.
Okay. We do that same thing here, I get 1, 2, and a half, 1, 2. If I do that with this one, I get 1, 2, 3, 4. Now I'm going to count backwards. I'll cross the line. 1, 2, 3, 4. So those 2 points, even graphically speaking, even though I can't really tell the numbers without counting, those 2 were ones that were flipped over each other. So were these. If I do that here, I get 1, 2, 3, 4, 5 and a half, 1, 2, 3, 4, 5. And I write it that one. These are the weird ones. This 4, 1, and 1, 4. That was what was spooking me. If you think of this as being blue first and this being pink second, then it would be 1 and a half, 1. If you think of this as being pink and you want to get to the blue, then it would be 1 and a half, 1. They just happen to be in the same place. Superimpose them. So this one's going to be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Arrives at that one. So what I'm saying here, once you get those lines, all the points here and all the points here when you switch X and Y, they are reflections of each other. The one that got flipped over, the blue, the pink one's buddy that goes with this blue one is this one right here. They reflect over the line Y equals X. They're the same distance from it. This is like a mirror for the both of them. All inverse functions do that. Reflect over the line Y equals X. What you're going to be dealing with mostly in this exercise are functions that are not lists of numbers. As a matter of fact, I don't even think they'll give you a list of numbers. What they're going to give you are functions like you're used to seeing as equations that have millions of points on them. Okay, so let's deal with some of those now and let's see if we can figure out what to do. So what we did here, we had a discrete number of points, 7 of them, and we flipped them over. Turned out that the inverse relation here was not a function, but we still called it F inverse. That's how you say it, F inverse. Now let's see how we can deal with functions that have billions of points on them. That's going to be tough. Okay, let's consider, all right, I'll consider theirs. F of X equals 3X minus 1. So, this is just a line. I hope you recognize it, and I hope you're very, very comfortable with knowing how to graph it. Are you? Especially in this form?
Yeah.
Okay. Wow, that purple really leaves a mark. Okay, so how do I graph that line? Just so I can see a picture of it, I'm going to link together the graph with the function as we go along. You go up where? Go down -1 on the y-axis, and then keep your pencil there, and then do what? Rise 3, run 1, connect them. So that line looks like this. If I'm careful to connect every third square like that, this one comes down 3, like that. Okay, so that's the equation of that line. If I have the line y equals x, this one right here that I drew with the purple before, how am I going to reflect that over that? And if I do, what will it look like? I'll draw it in pink. You see this point that we drew right here is actually going to show up over here on the pink one. And this one right here is going to show up right here. And it takes 2 points to determine a line. Remember that from geometry? Well, I just reflected those two. So it's going to look like this. And it's going to have a slope of what? 1/3. And it's going to cross where? The y-axis at... where does it cross? Did I draw that wrong? I don't think so. I went through the line. It's going to cross somewhere else, but let's see if we can figure out where it is on here. How many points are on that blue line? Millions. Too many to count. How in the world are we going to take all the points on that line and turn them all over to create all the points on the pink line? It's really slick. Watch this. Do you remember that this is often referred to as y? It's the output. It's the y value. So I'm going to rewrite it like that. I'm going to write it y equals 3x minus 1. Why do I do that? Because I don't want to drag this f of x all over. You could. It would be fine. I just want to use y though. And what you do, watch this. Remember I said there's millions of points on that blue line? How are we going to switch them all? Just like this. Now they're all switched. But to figure out the equation of that pink line, I need this one that I switched the x and y on. I've now switched all the points, just like that. Millions of points switched, just like that. But in order to be able to tell what this looks like and be able to graph it, I need to solve this for y. See, that's some work you gotta do. So once you've switched x and y, your next task is to solve for y. By first adding the 1, and then by dividing everything by 3, because that will isolate the y. Everything by 3. So I get, see that 1 right there? Can you see that 1? See it? So this is 1/3 x plus 1/3 equals y. And if you put it, just switch it over the equal sign, you get y equals 1/3 x plus 1/3. And that's supposed to be the graph of the pink line. And it is. See this right here? This is the origin from here to here. Do you see how it crosses at 1/3? And then from there you rise 1 and run 3. 1, 2, 3. It's right there. That is the line. Okay? And they reflect over the line y equals x, over that kind of purplish line right there. But this is how you go about finding an inverse. You take the function. I would, if I were you, when I write it down on my paper, change that f of x to y if it's not already, so that you're only dragging around a y, and it looks more familiar anyway. So rewrite it this way. So this is exactly the same as this. Then switch x and y and resolve the thing for y. The graph of this one and the graph of this one will reflect over the line y equals x. And by the way, there's one more step, and that is to come back now and call that new y f inverse. To write down the answer. You need to refer back to the form that it was offered in. This was offered as f of x. You need to finish it by saying f inverse of x equals this new y. Call it what it is. But you can use y in the interim to not have to drag around that so much. Okay, let's try doing one that's a little rougher. Let's say f of x is x squared. And they put this funny thing on there, not just to give you grief, there's a reason. They say f of x equals x squared for x's which are greater than or equal to 0. You go, why would they do that? You'll see in just a minute. Just stay with me for a second here. If I go to find the inverse of f, first thing I'm going to do is write it down as y equals x squared. Then the next step is to switch. You see it? And the next step is to square root both sides. And we should probably lead off with something involving f. So I'm going to flip those over, and I'm going to have f inverse of x equals root x. Which kind of makes sense, because the inverse of squaring is square rooting. Okay? Now if we graph both of these, this will become important. If x was greater than 0 here, what is that describing? Domain or range for the original function?
Domain.
Domain. Then that's also a description for the range of this one. This one is saying for y greater than or equal to 0, because it's switched to being a range now. It's the same restriction. It's still a 0, greater than or equal to 0 restriction. But here it was x's that were restricted, here it's y's. Now this is going to seem kind of subtle to you, and you're going to probably, without actually showing me because you're not insulting people, probably going to roll your eyes, but not really. But it is true. If I graph that original function in blue, x squared for x greater than or equal to 0, it looks like this. Only that, because when x is negative, I'm not graphing those. Those would be the other side coming up like that, right? I graph the line y equals x because that's our reflector. And you take a few points and jump through either by counting or just graphing that root x, which turns out to be like this. This one's going to stay here, and so is this one. This one's going to go to here. That's a diagonal, goes a diagonal there. This one's going to go 1, 2, 3, 1, 2, 3. It's going to be right there. Besides that, I went out 1, up 1, out 1, up 3, out 1, up 5. To do this one, I'm going to go up 1, out 1, up 1, out 3, up 1, out 5. Because it's the inverse, it's reversed. Okay? Now, had we not had this restriction on there, then this graph would have turned out like this. We would have included everything that we have, and it would have turned out like that. And this graph would have turned out like this. And can you see that the blue one? Well, I haven't told you this. Are you guys all familiar with the vertical line test? Vertical line test for functions. It says that if it is a function, then any vertical line that you draw will only hit it once at the most, maybe not at all, but never more than once. Can you see that the blue one is a function, but the pink one is not? So if it says to find the inverse function, and that word function is in there, then this restriction that I erased up here is important. Because if not, then you're going to have to consider f inverse as being a plus or minus, which is really two functions, because that will give you the bottom half. Or if it's just the principal square root function, which it should be to make it a function, then the original up here has got to be only the positive stuff, so that we get this. Now, if you look at the pink, that is a function, right? But it's not a reflection over this line of this blue thing unless I also take that off. Now it's a reflection of the line y equals x, and they're both functions. You see what's kind of important? Okay. And sure enough, the y's of my inverse, the y values are start at 0 and go up. They don't have anything down here because the domain and the range switch places. Okay, let's try another one. Oh, this thing. You guys all know about the vertical line test. You said, right?
Yeah.
Okay. Can you extend that in your minds to horizontal line test? So if I have a regular old parent function parabola, do you think do you think that's a function? Because it satisfies the vertical line test. Is it now this is the trick, this is the words, is it a one-to-one function? The answer is no, because it fails the horizontal line test. Any horizontal line you draw, there are several that will hit it more than once. A one-to-one function has unique x's because it's a function. It also has unique y's, and these don't have unique y's. This y value is used right there and right there, which means it fails a horizontal line test. So a parabola is not a one-to-one function. It's a function, it's not a one-to-one function. Why is that important? Because if you can tell that this is not one-to-one, then it's, then its inverse will not be a function, because if this fails the horizontal one, this will fail a vertical one. So you can tell whether the inverse will be a function or not by just looking at the original function. Okay, this one's inverse won't be a function. That one will be. That's one-to-one. Here's another example of a one-to-one that doesn't need a domain restriction. It's the cubing function, looks like that. Its inverse looks like this. And it's a reflection of the line y equals x. This one right here that stands up tall is x cubed. This is cube root of x. And both are the original function. I'll erase this so you can see it. The original function, x cubed, is one-to-one. It's a function. Also satisfies the horizontal line test, which means its inverse will be a function. You follow? Okay. So that's what they've got for you on example 4, except for they've got a transform one. They've got 2x cubed plus 1. So here's the function. Oh, I'm off screen. I better go here. Sorry about that. I hope you didn't get to it because I wasn't paying attention. If you need help with what I just said, let me know. Horizontal line test behave like vertical line test. Okay, so if I have this function, f of x equals 2x cubed, is it plus 1? In example 4, yeah? Okay. If I want to find the equation of the inverse, first of all cubed functions behave like I just showed you. They may be moved up, down, stretched, shrunk, reflected. They all behave the same way. They'll all be one-to-one. Cubed functions are always one-to-one. So I can expect a function to come out of this. And here's how I'm going to start. Y equals, when I do the inverse, y equals 2x cubed plus 1. I want to switch places. X equals 2y cubed plus 1. Now I got to solve for y. Kick the 1 over. Divide everything by 2. And cube root it. I mean, sorry, I switched that to 1. Wow, that was pretty tricky. Which is f inverse. I should call it what it is. It's the cube root of 1/2 x minus 1/2. Why don't you try graphing that in your calculator? Both of them. Put one on y1 and one on y2. Also, in y3, graph the line y equals x. See if it's a reflection. This is what it looks like in a standard screen for those of you watching. That's the line y equals x in there to show that it's a reflection. Did you get it reflected? It looks slightly distorted. What do? On your window, change the y's to go from -7 to 7, and it won't be that way. It'll look more like the reflection is supposed to be. So if you change the y's so they get spread out like the x's, this is what you get. It's only slightly different, but it's a little bit better. It looks a little more like a reflection. It's not bent or distorted. Okay, so that's verification when you graph it. It's a verification that we didn't make any mistakes from here to get this. We didn't make any algebra mistakes. Everything was good. Even though it turned out pretty ugly looking, it's still correct because of the way it shows on the calculator. So that's just a check. Okay, I think I have, well, there's two more examples. I want you to take a look at example 5. It says, consider the function 2 square roots of x minus 3. That function right there is only 1/2 of a parabola, right, that opens out to the right, because this is positive. You may not know exactly what it looks like. It's going to go right 3 and be a little fatter than usual because it's going to be vertically stretched by 2. Can you recognize that? Okay, so it's gonna be something like this. That actual graph's going to come out 3, and it's not going to open up like this. It's going to open up more like that. It'll be a little bit fatter. Okay, that's all I'm interested in for right now. So now I'm going to say this is y equals 2 square roots of x minus 3. I'm going to switch places. X equals 2 square roots of y minus 3 because I'm on a hunt for its inverse. And I've got to get at that y. I've got to solve for y. So the first thing I'm going to do is get rid of that 2 by dividing by 2. Everybody okay so far? Because this next part is routinely missed by people. Did you understand what I did there? Everybody clear or not? Yes? No? Yeah? You okay? Okay. Then I've got to square that thing off there to get at that y. And when I square it, I have to square the entire thing, which is 1/4 x squared. Not just 1/2 x squared. You got to square the 1 and the 2 and the x and get 1/4 x squared equals y minus 3. And so you get 1/4 x squared plus 3 equals y, and we call it f inverse. However, there's a big however. See that graph I have of the original function? Do you see how its domain is y0? I'm sorry. Do you see how its domain is x's are greater than 3? There's no x's behind 3 that are expressed, right? So in a natural way, without actually having to write it here, and if you see the graph, this is this guy's domain, and it's important to consider it because that's going to be this guy's range, which is y greater than or equal to 3. What's this one's range? This original one's range. What is his range? Talk about the y values that are expressed in the graph. What is it?
Y is greater than 0.
Yeah, greater than or equal to 0. What's the domain of this one? X's are greater than or equal to 0 because domains and ranges switch places. Okay, are you ready? You understand? Okay, now I'm going to show you a little trick on your calculator. This is really important to consider because if you don't, let's pretend that you forgot to consider that. Then what you're going to do to check on your graphing calculator, like I just showed you, you're going to graph these two functions, the original, which is 2. Do it with me. 2 square roots of x minus 3. And in y2, we're going to put 0.25 because that's 1/4 x squared plus 3. And in y3, put y equals x so you can see if they reflect. So we're going to forget about domain and range and see what happens. We're going to graph them. And that isn't quite a reflection, is it? This is what you get if you graph them straight up without any restriction. And one is not a reflection of the other because the one above, the y equals x, it's got more to it. That's the reason why this is really important. The domain of this one has to be restricted to x's which are only greater than 0. And believe it or not, you can make your calculator do that. To stop a function at a certain location. You want to know how? You do? Okay. It's kind of tedious. Here's what you do. I guess we can do it over here. Can you guys all see this? Can you see this over here well enough? Okay. Here's the way it looks in your calculator. To do it to this one, we have y1 equals. And then you need to start with a parenthesis, and it should look like this, 2. Oh no, it's this one that needs to be restricted, right? So it'll be in y2. Sorry. It's in y2. Because that's where this one that needs restricting is. It's in y2. So I'm going to put 0.25, because that's a quarter, x squared plus 3. And I'm going to close that. And then I'm going to write divided by. And open another parenthesis. And I'm going to write in there x greater than or equal to 0. And you're going, where do I get that greater than or equal to? I'll show you in a minute, but you need to get this far where you have this in parentheses, the whole function in parentheses, divided by parenthesis x. Get to there, and then I'll show you where to find that. Is everybody there? I got to get to there. So I got to scoop that into parentheses. The whole function, because we've got to divide the whole thing. Divided by parenthesis x. Okay, here's where you get these symbols. It is in the calculator above the math key, right here, just above the math key, right here. See the math key? Right above that it says test. So go second and the math key, and it gives you that list. Go and get the one that says greater than or equal to. It's the fourth one, number 4. And so put the greater than or equal to, typed it in there, and then put a 0 and close that parenthesis. And hit graph. And it will stop that parabola starting at 0 instead. Means it's only good for x is greater than or equal to 0. Now it looks like a reflection. Doesn't it? Yeah? We don't have that extra piece over here. So it's really important that you consider the domain and range, especially, and I didn't make this a big deal, especially the range of this one, because it becomes the domain of this one. Because of the switching around. And so sometimes, if there's a natural range restriction here, it was natural because it's from 0 up. You have to impose that restriction in the domain of your inverse. So that we go, starts at 3, and only the positive ones are expressed. That way it's graphed over the line y equals x. Otherwise, if you get this piece without this restriction, it won't be a reflection. There's a way to make your calculator show that. See, looks like that. When you restrict the x's on the inverse. How you doing? You okay so far? Lots of new stuff today. One last thing. One of the questions they're going to ask you on the exercises is, here's a function, they'll call it f probably. They'll say, here's another function, they'll call it g. And they will say, are these inverses? Prove it. And when that happens, folks, there's one way that most kids attack this, and it's wrong. Because I haven't told you how to prove that they're inverses yet. That's the last concept. A lot of people will say, okay, well, here's, if I give you f, if I give you a function like this, f of x equals 3 square roots of x minus 2, and they might give you a g like this, and you say that that's maybe 1/3 x plus 2 squared, something like that. And you might look at that, first of all, and say, well, the 3's been inversed, the plus sign, or the negative sign's been inversed, the square root's been inversed. I think they are. That's close. And here's another way to not prove this. You do it this way on the test, you won't get any credit. People say, well, what I will do is I will find the inverse of this and see if it's g. Bad way to go. Not the way you... So you might find that inverse and you say, okay, well, that's x equals 3 square roots of x minus 2. Oh, y. And then go about solving for y. That'd be 1/3 x. Third, things are making sense. Equals the square root of y minus 2. Square both sides. That gives me 1/9. Oh, I lost it. X squared equals y minus 2. And so we get f of x, if I go one more step, is equal to 1/9 x squared plus 2. You say, nope, they're not the same. They're not inverses. And it's true. These aren't inverses. But this is not the way to prove it. And if you go about it that way, you won't get any credit. Here is the way you prove two functions are inverses. You have to do this. F composed with its inverse has to equal x, And F inverse composed of F has to equal X. You have to prove this. You have to compose them both and get X both times. If either one of them fails, you're done. You say they're not inverses. I could show you how it fails with these if you want. You want to see? You want me to show you without all of this junk right here? This is the wrong way to do it. Don't do it this way. If I was trying to decide if these were inverses of each other, you're looking like you're kind of convinced. You got a reciprocal, you got a change of sign, these are all inverse things, and you're saying, I bet they are. So here's what you do. You say F composed with G. The question is that equal to X? That's what you're trying to figure out. Because this is F, we suspect this is F inverse. We're calling it G. Do you see how these match up? Okay. So what we do is we take F, and every place there's an X, we replace it with 1/3 times X plus 2 squared minus 2. Remember that stuffing in function? I took G, which is this junk right here, and stuffed it in for X and F right there to see if it actually turns out to be X. So here we go. We have to start cleaning it up. It's kind of a mess. You square that out, it's going to be 1/3 times X squared plus 4X plus 4 minus 2. That's going to be 1/3 X squared plus 4/3 X plus 3 minus 2, which is 1/3 X squared plus 4/3 X. 4/3 minus 6/3 is negative 2/3. F composed with G is this ugly thing. You think that's X? You think is there a way that that's going to have a value of X? Nope. So that failed. You say, nope, they're not inverses. Let me show you a case where it does work, where we compose them and we do get them to both be X. Consider F of X equals 3X minus 1. And G, which we suspect may be its inverse, is X plus 1 over 3. Evidence is pretty strong that these are, because if you know anything about inverses, that minus got changed to a plus, that timesing by 3 got changed to dividing by 3. It's likely these are inverses, but that is certainly not a proof. That just gives you evidence that you probably will work this out. Then we had the same evidence there, and it wrote that crap. That was garbage. This might work out. It actually will. Watch. I want to figure out what F composed with G is. That's going to be, I'm going to take F, and every place there is an X, I'm going to replace it with X plus 1 over 3. Did you see that plug in? See that stuffing? Now we clean it up a little bit. We get, oh, look, the 3's cancel. This is on top, this is on bottom. And I end up with X plus 1 minus 1. Oh, so far so good. Is that enough? No. That's evidence that you need to continue. One composition turned out to be X. You have to show the other one as well. So we're going to do G composed with F and see if we get X. You don't just get the same thing. You get X if they are inverses of each other. So we take G, which is right here, and every place there's an X in G, I'm going to write 3X minus 1. Did you see that? That X right there got replaced with 3X minus 1. See it? Stuffing? Yes or no? You following what I've done? We clean it up. This one's even easier. This negative 1 and positive 1 add up to 0, and I end up with 3X over 3, which is X. Therefore, and this is the way you write therefore in math. Therefore, F and G are inverses. This is your evidence, and this is your conclusion. But you have to compose the two of them together and get X. I don't know if this will make any sense to you or not. But do you remember I told you yesterday, whenever you do something with two functions, it creates a new function. It's like F plus G or F composed with G. This function, this is a new function that ended up being X. In other words, right here we had a new function's Y equals X. Here, this new function we created is Y equals X. How come? Because if they are inverses, they take each other back to the reflection line. Y equals X. If they are inverses, they take each other back in the inversion and return each other to that line of reflection. That's why it has to be Y equals X. Pretty crazy. I know that's kind of fuzzy math, but that's the reason why it has to equal equal x, because the new function has to have y equals x.
Will it always equal x?
Yes.
Y equals x?
Yeah, it's not that they just have to be the same thing, they have to be x. If they're anything else, all bets are off and you're done. And they're not inverses, okay? Did you follow all that? That's a lot of stuff today. Good luck. Comes the assignment. There's 30 questions today. And the assignment is, for those of you doing it on paper, are you ready to write? It's 5 to 19 odd, 22, 23 to 29 odd, 31 to 34, 35 to 45 odd, 49 to 51 odd, and 55 to 58. Good luck. See you, bye.